I'm left with two more lectures. So I'll see what we can cover. So mainly the proof of Schur's lemma I'll do in today's lecture, and then I'll try to cover spectral theorem also for normal matrices, and then there will be one more lecture. So we'll see what we can do. Okay, so um, let me remind you that there will be a quiz tomorrow at 3 o'clock, as I already mentioned in my email, and I had already announced this quiz. So this is an extra quiz. Like at the beginning, I had announced that I will take three quizzes, but since some of you were like could not perform well in the first quiz, so and some of you were absent also in some of the quizzes. So for them, it would be an opportunity to score good, to like make up for whatever they have not done in the earlier quizzes. Second thing is that the major exam would be on 17th of November, and it is I think in from 9 to 12 slot. So I'll send an email regarding that. In the major exam, the syllabus would be everything whatever we have covered in the course, and it would be based on Gradescope only. I mean, it would be online. So for those who are already in the campus, so how many of you are in the campus? Can you tell me?
Three, sir.
Who is so so you are in the campus, right?
Yes, sir.
Okay, and who else? So I saw that there are there were two names in that list. I think Tanvi is also in the campus.
Yes, sir.
So you two are in the campus, right?
Yes, sir.
Okay. So I mean, you went for like Diwali break, and you are back now.
Sir,
You
I
are
am
back
in
in the campus.
right now, but Tanvi is in hostel right now.
You are not in the hostel, but Tanvi is in the hostel. Is
Nahin,
it?
sir. I am in hostel.
Sir, I'm traveling to
Okay.
Delhi. I'm right now in train.
Oh, I see. Okay. So for you two, I'll see what we can do. So if I follow the instruction, according to the instruction, for you two, there would be an offline exam at the same time. So the others would be writing the exam online on Gradescope. But since you two are in the campus, so you have to like appear in person for the exam. So that also I'll send an email and mentioning all the details. All right, so let us start today's lecture. So in the last lecture, at the end I stated the result of and the statement of Schur's lemma. So the Schur's lemma says that every matrix is every complex matrix of size n cross n is unitarily similar to an upper triangular matrix, and today we will see a proof of it. We have already done a similar result where we proved that every matrix is similar to an upper triangular matrix. Here we can say more than that, that similarity matrix, that similarity transformation, or the matrix that um, achieve this can be chosen to be a unitary here. So let us start today's lecture by proving the Schur's lemma. So let me write this statement again, and then we'll see how to prove. So the proof is very easy. So I'll just give you some idea, and then you can complete the proof. So Schur's lemma. So what is that? So suppose that we have a matrix A of size n cross n over C. Since it is a matrix of size n cross n over C, then we know that it will have exactly n eigenvalues. So let us call that these eigenvalues as lambda 1 to lambda n, with eigenvalues lambda 1, lambda 2, and so on up to lambda n. These are in any order, any prescribed order. So you can arrange whatever order you want. Then, depending on this order, then you can find a unitary matrix. So then there exists a unitary matrix U of the same size such that such that U star AU is equal to T, where T is the upper triangle. T is upper triangle. And let us denote the entries of T as Tij. Okay, with the ith diagonal entry of T is lambda I. So with Tii is equal to lambda I for all I equal to 1 to n. So what it says that you arrange these eigenvalues in any order, lambda 1 to lambda n, and depending on this order, you can find a unitary matrix U such that U star AU is equal to T. Not only that, the ith diagonal entry of T would be lambda I. You can find such a U. Now, how to achieve this? Proof is not difficult. Since A is a matrix and lambda 1 to lambda n, these are the eigenvalues, these are given. So what is given? So we are given that this matrix and lambda 1, lambda 2, these are the eigenvalues in some order. So these are the eigenvalues. Okay. Now A is a complex matrix, so we know that these are the eigenvalues. So let us take the eigenvector corresponding to first eigenvalue lambda 1. So let us suppose that let x1 is not 0 is an eigenvector. So let x1 be an eigenvector corresponding to eigenvalue lambda 1. So let x1 is a vector such that ax1 is equal to lambda 1 x1. And we can, without loss of generality, we can assume that the length of x is 1. So you know what is this? This is actually, so maybe I should not write this 2 here because we are using a different notation. So what is this? This is x star x square root. Okay, so this is 1. So this is with respect to the standard inner product on C. All right. Now we have a first vector which is of unit length. So what I can do, I can choose or I can extend this vector to an orthonormal basis of Cn. So choose y2 to yn such that this set x, x1, x1, y2, y3 and so on up to yn, this becomes an orthonormal basis. So this becomes an orthonormal basis of Cn. This I can always do, right? Because it's a vector of unit length. So how to do that? You first, so can you tell me how to get this y2 y2 to yn so that this becomes an orthonormal basis? So how to find this y2 to yn such that this becomes an orthonormal basis? So any idea
First
how to
find the best.
extend this
So
x1?
find the value there.
Sir, y1 equal to x1
Uh,
and y2, y3 and yn chosen by Gram-Schmidt process. Then
so
also
you are saying
normal.
that first, yeah, first extend this basis, this x1 to a basis, and then you orthonormalize
Yes,
it
sir. Yes,
using Gram-Schmidt.
yes, yes, yes.
Yeah, so you can always do that. Okay. So let us set this. So you remember what we want? We want a matrix, unitary matrix U, such that U star AU is T. T is upper triangular. This is what we want. So this is what we are trying to do. So, and we have to find this U in such a way that the diagonal entries of T are so the ith diagonal entry is actually lambda I, because we know that when they are unitarily similar, then they have the same eigenvalues. So the ith eigenvalue of T is actually lambda I. So Tii is equal to lambda. Okay. So now using these vectors x1 to x1, y2 to yn, using these vectors, I will construct this u1. Let's say u1. This is a matrix where the first column is x1, second column is, let's say, let me write it in this way. So the second column is y2, the third column is y3, and so on up to yn. So this is basically uh, an n cross n matrix. And is it unitary u1?
Yes, sir.
Yeah, because the columns are orthonormal. So this matrix is n cross n matrix, unitary matrix. So this u1 is unitary. Also, what you get when you do AU1? When you do AU1, then it would be, if you multiply column wise, it would be, the first column would be AX1, then AY2, then AY3, and so on up to the last column would be AYN of this product. But lambda x1 is, AX1 is just lambda 1 x1. So the first column is lambda 1 x1, second is ay2, and then for other columns we don't know, but for the first column we know that because we have chosen this x1 as an eigenvector corresponding to lambda 1. What can you say about u1 star au1 when you multiply u1 star from left hand side? So what is u1 star? U1 star would be, if u1 is this one, if you take the star of it, then what it would be? It would be x1 star, y2 star, and so on to yn star. This is u1 star. And then AU1 is this one, lambda 1 x1, AY2, and so on up to AYN. Now can you tell me what is the first column of this product? Right hand side. So what would be the first column of this product?
Lambda 1.
Just lambda 1. This is a matrix. U1 star is a matrix.
Lambda 1 0 0
U1
0.
star is yeah. So this is lambda 1, the first column, and the rest of the entries in the first column would be 0. So if I write this in this way, so the first column is lambda 1, and then all the entries are 0. Why this is? Because when you multiply, the first entry is lambda 1 x1 star x1 here, but x1 star x1 is 1, so it is lambda 1. Then y2 star x1, the second entry would be lambda 1 times y2 star x1, but y2 yn, they are orthogonal to x1, so these entries would be 0. So this is what we have in the first column. What about the other columns? For other columns we don't know. So what we can say that the first row, the remaining entry in the first row are, let's say, they are denoted by star. There are some entry we don't know. And then there would be this matrix of size n minus 1 cross n minus 1. So let us call this matrix as A1. Okay. So this is your U1 star AU1. Okay, so let me write it again. So this is U1. This is U1 star AU1. Okay. Now what can you say? So now A is unitarily similar to this matrix. So from here you can say that A is unitarily similar to this matrix. So this matrix A1 is not upper triangular. If this is upper triangular, then we are done, but this is not. But what we know is that the first column we have we have created in such a way that this is now, at least the first column is in the upper triangular form. And the eigenvalues of A, what can you say about the eigenvalues of A and eigenvalues of this matrix?
Are same.
They are same, but
Yes, sir.
they are like lambda 1 and eigenvalues. What would be the eigenvalues of A1? So if you look at this one, then you can say that the eigenvalues of, from here, what you can say, from here you can say that the eigenvalues are, you know that they have the same eigenvalues. So if lambda 1 to lambda n are the eigenvalues of A, then lambda 1 to lambda n, they are the eigenvalues of the right hand side also, this matrix also. Now we can say that lambda 1 uh, in this form, the matrix is in this form. So the eigenvalues of this matrix in the right hand side is the union of lambda 1 and eigenvalues of A1. But we know that the eigenvalues of this matrix are lambda 1 to lambda n. So the eigenvalues of A1 would be, what
Lambda
would
2,
be the eigenvalues?
lambda
Yeah,
n.
lambda 2 to lambda n. So then we can say then the matrix A1 has eigenvalues lambda 2 to lambda n. Okay. Now do the same thing whatever we did here up to reach up to this step. Do exactly the follow exactly the same step and obtain a similar thing for A1. Okay, so what I'm saying is that now let me write this. So let x2 is in Cn minus 1 such that, because now this is a n minus 1 cross n minus 1 matrix, I can again do the same thing. I know the eigenvalues. So what I will do, I will find some vector, let's say x2, such that the length of x2 is 1 and a1 x2 is the eigenvector corresponding to eigenvalue lambda 2. Okay, so do it all over again like we did in the same way. You find u2 in n minus 1 cross n minus 1 over C unitary matrix such that u2 star a1 u2 is equal to lambda 2 of this form 0. This is some entries in the first row of this matrix and then the submatrix A2. If I do exactly the same thing as I did to create A1, if I follow exactly the same step, then I will get this one, right? Now, if I choose, now you can see here, this is of size n minus 1, sorry, this is of size n minus 1 cross n minus 1. Our original matrix of size n cross n. Now, if I somehow combine this u1 and u2, then what I can do, if I somehow combine u1 and u2 in such a way that if I combine these two things, then at least I can create two, I can make the first two columns in the upper triangular form, right? So what I'm saying is that using this information, can you find something unitary matrix, maybe not exactly u2, but some other matrix such that when we multiply, uh, when we apply that matrix on u1 star a u1, so a1 star a u1 is this one. Now can we find some matrix, let's say v1, such that when I multiply v1, when I do it in this way, then I have lambda 1, then lambda 2, rest of the entries in the two columns are 0, and then we have this one. So can you tell me what I should choose here, v1, so that I have something like this?
It is U2 itself.
No, u2 is of size n minus 1 cross n minus 1, and u1 star a u1 is of size n cross n. So
Yeah.
u2, exactly u2, I mean the same u2 won't work. You have to do something.
U2 के कॉलम में 0 0 एंट्री.
सिर्फ 0 0 कर देंगे तो नहीं आएगा. So you want to add one more column, but not so see, you have already created zeros in the first column here. You don't want to disturb this structure, but whatever you want to do, you want to apply this information on this matrix A1 here. So what you can do, so whatever, so see here, if I choose this matrix, let's say V1, so let me write it here. So choose V1 as let me write V2. Let's V2, just a notation, V2 as 1 0 0. So that means the in the first column, the first entry is 1, then the rest of the entries are 0 in the first row in the first column, and then you put, let's say, U2 here. Now this is of size n cross n. So see here, this 0 is actually the entries. These are denoting all the entries, remaining entries in the first row, and these denoting remaining entries in the first column. Now you look at this one. Is V2 unitary here?
Yes, sir.
Why?
Because U2 is unitary, then V1 जो फर्स्ट कॉलम इंसर्ट कर रहा है वो तो कोई इफेक्ट कर ही नहीं रहा है, वो आपस मतलब ऑर्थोनॉर्मल भी है, मतलब नॉर्मल भी
Right,
और फिर सबसे ऑर्थोनॉर्मल भी है.
right. So V2 is a unitary matrix, and now if I like multiply this V2 here, then I achieve this because the first column is is like E1. It's 1 at one position, and the other entries are 0. So it will not disturb the first row and first column of this matrix here. Or not this one, but this matrix here. So this way we have created. Now you can see that the two columns are in the form of upper triangular, in the form of upper triangular matrix. But we can repeat the same process. Continuing the same process will result in unitary matrices, let's say V3, V4, and Vn minus 1, such that when we multiply these matrices from right and left, we'll get an upper triangular matrix. So this you can now complete. So continuing this process will result in unitary matrices. So this way we can create construct unitary matrices, let's say V3 up to and so on up to Vn minus 1, such that when we do this A1, then when you apply V2 star from left hand side and then V2 and so on up to Vn minus 1 star Vn minus 1. So then this will give us an upper triangular matrix where the ith diagonal entry of this upper triangular matrix is lambda I. So this is in the upper triangular form. So this is your matrix T. This is you can call as U star, and this you can call as U. So the product of unitary matrices is again unitary. So let us call this as U here, U star, and this would be U. So you are done. The result is proved. Now this, as I already mentioned in the earlier class also, in the previous class, that this result is very important in so many applications. One result, one application of this result is to prove the Cayley-Hamilton theorem. This theorem is named after the names of two mathematicians. I think Arthur Cayley and Hamilton. I forgot the first name of Hamilton. So this result, Cayley-Hamilton theorem, this can be proved easily by using this Schur's lemma. And then there are many other things which you can do in theory as well as in like in practice. You can use this result in order to like simplify your problem. So if you have a matrix, then you know that you can always unitarily upper triangularize in theory. And once you have upper triangular matrix, then things become more easy to handle, right? So in place of a general matrix, if you have an upper triangular matrix, then you can say many things about this. You can quickly tell what are the eigenvalues. In theory, at least you can say eigenvalues, trace, determinant. You can solve the system of equation of an, if the matrix is upper triangular. So there are many things you can do. So let me prove this Cayley-Hamilton theorem, because this is also one of very like important result in matrix theory. So we can do it. We can write it as application of Schur's lemma. You will see that the following results I will prove using these Schur's lemma. So the proof becomes very easy. Not only for this Cayley-Hamilton theorem, but uh, for for other results also. You will see that. So before we start, let us make this observation first. Before I give the statement of Cayley-Hamilton theorem, let us make this observation. Suppose that we have a matrix R. This is just some matrix product of two matrices, okay? But the matrices have this form. So let's say we have a matrix R where the first where it has this block structure. Okay? The first block is of size k cross k. So this is of size k cross k. It's a zero block, so it's a zero matrix of size k cross k, and the other entries of the first, like the these two entries also zero. So basically the first k columns are zero. Then here we have something we don't know. So here we have like k cross n minus k, and then here we have an upper triangular matrix. Okay, so this is the structure of R. So it has the first k columns are zero, and then we don't have any structure on this. These are some entries in the remaining entries of the first k rows, and then this matrix is upper triangular. So that means these entries are zero. Okay, and suppose we have another matrix, let's say T, which is of this form. It is also has this block structure where the block is upper triangle. Let's say this one. So this is upper triangular of size k cross k. The same matrix is size k cross k. And the remaining entries in the first k columns, they are zero. Then we have some entries here, the remaining entries of first k rows. Then we have this entry 0 here, one entry 0, and the other entries we don't know, but this matrix is again like in the upper triangular form. So we have this form, this matrix. So it has almost a similar structure as R. So instead of here 0, we have an upper triangular matrix of size k cross k. Other structures are same, except except the fact that here this entry, the first entry in this 2 cross 2 upper triangular matrix is 0. So I am saying is that that is tk plus 1. If I denote the entries of t as tij, then you can say that this entry is 0. The k plus 1 diagonal entry, k plus 1 diagonal entry of t is 0. Okay, these are the two matrices R and T. Now, can you tell me what would be the product of RT? Look at this and tell me what would be the product of R and T. Tell me what would be the first block.
First block is 0.
First block is 0, 1 block. What about here? What can you say about this position? 2 1 position. This is also 0. Okay. What about 1 2 position?
Star.
1 2 position is star. Can you say something more than that?
So it's upper triangular.
It is not upper triangular, but what you can say, you can verify that this column, the k plus 1th column, can you say about this k plus 1th column? So these are k cross k matrices. So the first k columns are 0. What about the k plus 1th column of this product? Look at this product. What can you say about the k plus 1th column of this product? Yeah,
Zero, sir.
k plus 1th column is 0. If you look at the product here, you will see that this column is 0. Can verify that, and then this matrix remain in the upper triangular form. Okay, so this is the observation. We will use this observation in the proof of Cayley-Hamilton theorem. So now let me write statement. So the first application, there are many applications, but you can see this as a first application of Schur's lemma for us. Cayley-Hamilton theorem. So what it says that if we have a, so see what Cayley-Hamilton theorem says, it says that if you have a matrix A, no matter whether it is a real matrix or it's a complex matrix, if it is a real n cross n, if it is a matrix of size n cross n, then this matrix satisfies its own characteristic polynomial. So what does it mean? It means that if suppose, so let me write this first. So we will prove this result. So as I mentioned that no matter whether the matrix is real or complex, you can, this result is true for both the matrices of size n cross n. But here in the class, in this lecture, we will prove it for complex only, because then the proof is easy, and because of the Schur's lemma, because it is true only for um, like complex n cross n matrices. Schur's lemma is valid for that, and using that lemma, I want to prove this Cayley-Hamilton theorem. So we'll prove it only for complex n cross n matrices, but this statement is in general also true for in general true for real also for real matrices. So let us denote the characteristic polynomial of matrix A by PAT. So let PAT be the characteristic. So you know what is the characteristic polynomial? It is like lambda I minus, oh sorry, determinant of lambda I minus. So I think you know that. So let this be the characteristic polynomial of A, where A is of size n cross n over C. Then what Cayley-Hamilton theorem says, it says that then this is 0. Okay, so what is the meaning of P? So this is the polynomial in A. This is a polynomial. So this was a polynomial in T, but when you replace argument T with A, then this becomes a polynomial in A, in the matrix A, and this is 0. So what does it mean? It means that if you have, let's say, PATs of the form, it's determinant of lambda I minus A. This is the characteristic polynomial. So it is it's a monic polynomial, so it is of the size of this form, lambda n plus a n minus 1, lambda n minus 1, and so on. Right? Now, what would be PAA? PAA would be when you replace lambda by A, so it would be a matrix of this form, an plus an minus 1, an minus 1, and so on. So just replace lambda 1 or lambda by, so this is n or lambda. So it is just this one. Now, what Cayley-Hamilton theorem says, it says that this would be 0. So every matrix satisfies its own characteristic polynomial. Here we will prove this result only for complex and cross n matrices. But the same result is also valid for real and cross n matrices also. Okay, so what does it mean? It means that every square matrix satisfies its own characteristic polynomial. Okay, so the proof is proof follows because of Schur's lemma. So how to prove this? So let us suppose that the characteristic polynomial, which is determinant of lambda I minus a, this is equal to, this is given by, since it would be a complex polynomial of degree n. So what we can do, we can write this polynomial uh, in this factors, and we know that this since it's a degree n polynomial, so it will have n roots. So I can write this polynomial in this factorization form, like let's say t minus lambda 1, t minus lambda 2, and so on up to t minus lambda n. Right? This I can do where this alpha is in C, not 0, and lambda 1 to lambda n, these are the eigenvalues of A, because we know that the roots of the characteristic polynomial are the eigenvalues of A, right? So this we can do. We have not used anything. This is because of the characteristic polynomial. We know that it's a degree n polynomial over C, and it will have n roots, and the roots are the eigenvalues. So let us denote them by lambda 1 to lambda n. So this gives us a factorization of this polynomial in this form. Now by Schur's lemma, what we know, by Schur's lemma, we know that there exists a unitary matrix U of size n cross n, such that this matrix A can be written as, so it's U star AU. So U star AU is equal to T. So where T you can sorry, T is of this form, lambda 1 to lambda n. This is a upper triangular matrix of this form, right? This is because of the Schur's lemma. So from here you can say that A is UT U star, using the fact that U is unitary. Okay. Now look at what we want to show. We want to show that P, this A satisfies its characteristic polynomial. That means when we want to prove this one. Okay. So let's look at this P, this polynomial in A. Now this A I can replace by this UTU star. So what it would be if you look at this one. So here I will just replace T by A, and since A is UTU star, so I will put in place of T, I will put UTU star. So what I get here is alpha times, the first factor would be UTU star minus lambda 1I, then the second factor would be sorry, UTU star minus lambda 2I, and so on up to the last vector would be UTU star minus lambda NI, right? Now what we can do from here, so it would be, I can write it as alpha times this, the first vector I can write in this way. I can take U common from left hand side and U star from right hand side. So for the first vector, the first term in this factorization, I can do it in this way. I can write it in this. Can I write it in this way? So this is for the first. Then the second term would be for the all the terms I can do it in the same way. So it would be U t minus t2I U star and then so on for all the terms. So the last term would be U t minus lambda ni U star. So why this is true? Because we know that U is unitary. So here I can, in place of I can write U star. Then I can take U from left, common from left hand side and U star from right hand side. And this is what I get. Now again, you see here. Now this is in the product. So this U star U, this would be identity in all these terms. So all these all the U's which are appearing in here in between, they would be gone now because they are equal to identity. So what we are left with is alpha times the first U would be there U. Then what we have is t minus lambda 1I, t minus lambda 2I, and so on up to t minus lambda ni, and then there would be U star at the end. Okay, but what is this here? If you look at this, so this factor here. This is the polynomial in T. So what you can say that this basically you can write it as U P T P A T U star. So what we have is that we have this one, right? Because you look at this one, what is PAT? You just replace, you change this argument T by the matrix T, and this is what you get, right? What we want to prove, that TAA, that means this polynomial in A is 0. That is equivalent to say that this if we show that this is 0, then this is also 0 because U is a invertible, it's a unitary matrix. So if we show that this matrix is 0, this is also a matrix. If this is 0, then we are done, right? So what we can do, so clearly this is 0 if and only if this is 0, right? But this is 0. PAT is 0 because of the above observation, and we are done. Now you tell me why this is true. Why PAT is 0? So we have already made this observation here. Look at here. And because of this observation, this is 0. So let us look at why this is 0. So the proof is over. I'm just convincing you that this whatever I've written, that is true. Why this is true? You just take, so you look at this PAT. What would be PAT here? Oh, sorry, this would be capital T. So why this is? So look at here. What is PAT? PAT is alpha times T minus lambda 1I and so on, T minus lambda ni, right? let's say t minus lambda 2i, the second term, and then the remaining term. Now let us look at the first two, the product of the first two term. So what is t minus lambda 1i times t minus lambda 2i in this product? And whatever you get, you multiply that with t minus lambda 3i and so on. So let us look at this one. What is this t minus lambda 1i? It is a matrix of this form. It will have 0 because t has T is an upper triangular matrix there where the first diagonal entry is lambda 1. So when you do t minus lambda 1i, it would be 0, the first entry. And since it is in the upper triangular form, so it remains upper triangular. Then you can write it in this way. Then this is the first row, and then this matrix here, which is in upper triangular form. What about t minus lambda 2i? It is also in this form. It would be like some one entry here. Then what you have? Then you have some entry here. Then the zeros here. But then since t minus lambda 2i, so the 2 entry would be 0, and then it remains in the upper triangular form. Right? Now you look at here, it is in the form of, if you look at this observation, these matrices are in this form, and therefore when you multiply these two matrices, the second column would also be 0 here. So as a result, when you multiply these two things here, what you get is that the first two columns are 0. Okay, the first two columns are 0. So this is what you will get. But then you multiply again with t minus lambda 3i, then you will get that when you multiply t minus lambda 3i here, then it would give you it would make the third column also 0. And if you keep multiplying from right hand side, you will see that at the end of this product, that means multiplying multiplying all these terms, you will get a 0 matrix. All the columns would be 0, and therefore this is 0, PAT is 0, and therefore PAA is 0. So every matrix satisfies its characteristic polynomial. Okay, so all right. Now this Cayley-Hamilton theorem itself is very useful. You can use it to find like the powers of a matrix. You can use it to find in calculating inverse of a inverse of an invertible matrix. So like write it here. So you can. So what is the use of Cayley-Hamilton theorem? You can use it to write powers like powers means a to the power k of a matrix size n cross n. You can write powers of ak powers of a as a linear combination of previous term like ia up to ak minus 1, and you can also use it in calculating inverse. For example, let me show you how to do this. So for example, if you look at this matrix, let's say 3 1 minus 2 0. So what is the characteristic polynomial of this? You can find that the characteristic polynomial of this matrix is t square minus 3t plus 2. Okay, and by Cayley-Hamilton theorem, now this is the characteristic polynomial. So by Cayley-Hamilton theorem, what we can say, Cayley-Hamilton theorem, we can say that PAA is 0. That means a square minus 3a plus 2i is 0. So, but what does it mean? It means that this implies that A square is equal to 3a minus 2i. So you can see that you can write it the second power of a in terms of as a linear combination of the the lower powers, and then you can use it like if you want to find a3, then what is a3? It's like you can do it in this way, and then what is this? This is a square. You know that it is 3a minus 2i. So it is again 3a square minus 2 times a. Then again you know a square is 3a minus 2i minus 2a. So when you do it, what do you get? 6, oh sorry, 9a. So what you get here? 9a minus 6i minus 2a. So it is actually 7a. It is 7a minus 6i. So this is a cube. So finding the powers of a also becomes easy if you use Cayley-Hamilton theorem. Okay, so now you can, instead of calculating a cube here this way, you can easily tell what would be a cube from here. Also, you can tell whether the matrix A is invertible or not if the constant term is non-zero. If the constant term in the characteristic polynomial is non-zero, then you can conclude that the matrix is invertible. So if the matrix is invertible, then you can easily find the inverse, right? So so if the constant term, this is very easy to see. If you just look at the characteristic polynomial, if the constant term in the polynomial is non-zero, then the matrix is invertible, because then you can say that 0 won't be an eigenvalue. So 0 is an eigenvalue if and only if matrix is not invertible. If 0 is not an eigenvalue, then the matrix is invertible. So if 0 is not an eigenvalue, when it is not an eigenvalue, when this constant term here is non-zero. So in this case, for example, this constant term is non-zero, so this matrix is invertible. So once you know the matrix is invertible, you can find inverse also using Cayley-Hamilton theorem. So if the constant term is non-zero in the characteristic polynomial of A is non-zero, if non-zero, then it implies that the matrix is invertible, or you can say A is invertible. And if A is invertible, then by Cayley-Hamilton theorem, what you can say from here? See here, if you look at this one, what you can say from here, you can say that a square minus 3a is equal to, or maybe you can write it in this way. You can say 3a minus a square is equal to 2i. But then if you divide it by 2, then what it would be? It would be 3 by 2, 3 by 2 a minus a square by 2 is equal to I. And then you can write it as 3 by 2 I minus a by 2 is equal to I. Now clearly, if this is the expression, then you can easily say that this would be the inverse of A. The inverse of A is 3 by 2 I minus a by 2. So you can also find, or you can also calculate inverse using the Cayley-Hamilton theorem. Okay. Now let me show you one more important result using this Schur's lemma. So this says that although we have seen that not every matrix is diagonalizable, right? We have seen several examples where the matrix is not diagonalizable. So not every matrix is diagonalizable. But what you can say is that although it is not diagonalizable, but it is arbitrarily close to a diagonal matrix. That means every matrix is almost diagonalizable. So I'm using it in a very vague language, but what I mean is that although the matrix is not invertible, not diagonalizable, but you can find a matrix which is arbitrarily close to this given matrix, and that matrix is diagonalizable. So that way you can say that okay, it is not diagonalizable, but it is almost diagonalizable, because you can always find another matrix which is diagonalizable, and it is arbitrarily close to this matrix. When I say arbitrarily close, then you can say that the length of the difference of these two matrices is very small. Or in mathematical language, you can say the following. So as a second application of this, so this is, you can say, as the first application of this Schur's lemma, and as a second application, there are many, but I have listed at 2, 3 here. So every matrix is almost diagonalizable. So when I say almost diagonalizable, it means that it is arbitrarily close to a diagonalizable matrix. So but mathematically, what we can say, that if we have a matrix A of size n cross n over C, let us denote the entries of A by Aij. Then arbitrary close means for any given epsilon, for any epsilon greater than 0, there exists another matrix B. Let us denote the entries of B by Bij. Another matrix B of the same size with with n distinct eigenvalues. With n distinct eigenvalues such that such that the the you remember what inner what is the notation I have used for this? What is this notation I have used for? This is less than epsilon. The length of A minus B. So this is the Frobenius inner product, or you can say this is the standard inner product with respect to the this is the standard inner product on the set of n cross n matrices. You remember what is this inner product on set of matrices?
trace of B
The
star.
standard. Yeah, so it is basically, so let me recall here. So recall that uh, what I mean by this is the trace of A star or A star A, both are same. So okay. So or in other word, you can say, what if you like calculate this length, the length of the difference of A and B. So if you calculate this, then what is this? This is trace of A minus B times A minus B star. Or when you do it, you can say that maybe let me put a square here so that the square root is gone, so the calculation becomes easy. So this is also equal to, like, when you calculate this, it is same as this one. Take the entry wise difference, take the square of the entry wise difference of uh, A and B, and take the sum for all the entries, and this is less than epsilon. This is the same thing. So this side here is actually this one. So now you can see that when I say arbitrary close, that means the entries of A and entries of B, they are very small, and they are very close to each other, because this result is true for any given epsilon. So however small you epsilon you choose, no matter however small this epsilon you choose, you can always find the matrix B with all distinct eigenvalues such that this is okay. I'll prove this result, but before that, let me tell you that why this is important, because now see, if suppose this result is true, I'll prove this. This is the proof is very straightforward. But if this result is true, then what it gives you? It tells you that okay, every matrix is almost diagonalizable, right? But then what else it says? It says that the set of invertible matrices, because you can see that with n distinct eigenvalues, and in fact you can choose this all these distinct eigenvalues, all these eigenvalues as non-zero. You can choose this. So you can say that the set of invertible matrices, or you can say that every matrix is close to a invertible matrix, arbitrarily close to an invertible matrix, or equivalently you can say that the set of invertible matrices is dense in the set of all n-cross n matrices, right? Set of all uh, invertible matrices is dense in the set of n-cross n matrices, or what you can say it is dense. So what you can say is that the probability of when you randomly generate a matrix, let's say in MATLAB. So if you randomly generate a matrix of size n cross n, then the probability of this matrix to be invertible is almost 1. So that means every time when you generate a random matrix, you will get a you will get an invertible matrix only. Or you can say that the singular matrices, singular means non-invertible matrices, they are highly sensitive. Sensitive means uh, when you like suppose that your matrix is singular, but when you enter the entries of this matrix in the computer, due to some error, if these entries are disturbed, then it becomes invertible. So the entries or the singular matrices are highly sensitive to the perturbation. So and therefore you try to avoid singular matrices because they are sensitive. So their behavior under perturbation becomes like very tricky to study. Okay. So because of this result, you can conclude several things. Like I mentioned, you can say that every matrix is almost diagonalizable. Every matrix is almost diagonalizable with distinct eigenvalues. You can say that every matrix is arbitrarily close to an invertible matrix. Or equivalently, you can say that every or the set of invertible matrices is dense in the set of all n cross n matrices. Or the probability of a randomly generated matrix is or of a randomly generated matrix to be invertible is uh, almost 1. Every time you will end up in generating an invertible matrix. Or singular matrices are highly sensitive because they are arbitrarily close to an invertible matrix. So if suppose you make some changes in, or due to some error, if there is a change in the singular matrix, then it becomes invertible, it becomes non-singular. So they are highly sensitive to the perturbation also. So so you can see that we can conclude several things for using this statement here. So let us prove this one.
Sir,
Yeah.
so your screen is not visible.
Sorry,
Sir, your screen is not visible.
screen is not visible.
Yes, sir.
Since when?
From now, sir.
Screen is from now only. Okay. Is it visible now?
Yes, sir.
Okay. So let us prove this result here, that for a given matrix A, we have to find this matrix B. So what is given is that the matrix is given and epsilon is given, and using this we have to construct this V such that it satisfies this relation is satisfied. the length of a minus b square is less than epsilon. So how to do that? So what we know, what we know by Schur's lemma, we know that there exists u unitary Schur's lemma, we know that there exists a n cross n unitary matrix U such that U star AU is T, which you can write as, which is upper triangle, okay, or maybe U star AU is upper triangular, right? So let us denote this matrix as T, where the entries of T are denoted by Tij. So this is the upper triangular matrix T. Okay. Now, what we want to construct B such that A minus B is less than epsilon. So, what is A here? A is actually a U T U star. Okay. Now, how can we construct such a B? Can we do that? I mean, can you guess something from here? How to choose this one? Keeping in mind that we want this to be satisfied. So, if I choose, let's say, if I choose alpha 1, alpha 2, and so on, alpha n, these are the scalars such that first this alpha 1, let's say t11 plus alpha 1, t22 plus alpha 2, and so on, tnn plus alpha n. That means the diagonal entries of t. So I am adding these scalars alpha 1 to alpha 1 such that these are all distinct. Can I choose such scalars alpha 1 to alpha n in C such that these becomes all distinct? These become all distinct.
Yes, sir, we can.
I can always choose, okay. And not only that, I will also put this restriction because I want this expression to be satisfied here. So what I will do, I will choose this alpha i's such that this is less than epsilon by n square. Why I have chosen it in this way? Because I want this relation to be satisfied. That is the only reason. So in place of, if in place of this length, that means it is actually norm. So in place of this norm, if I use some other norm, then also I will just modify my proof by choosing these alpha i's so that this relation is satisfied. So here, since I have used this length, this is also known as Frobenius norm. So I've used this norm, so I will choose this alpha I so that they satisfy this. And now using this alpha i's, I will construct this matrix, let's say E, which is a diagonal matrix with where the entries of E are diagonal entries of E are alpha 1 to alpha n. So this is diagonal. E, I will construct this matrix E. And now you look at this matrix B. What is B? Sorry. So what is B? So I want A minus B. So what I want A minus B. This should be less than epsilon. So A is ut u star minus B. So what I'll do is that I will choose this B this way. So let us consider B as A plus u e u star. Now you can see that when I do this B minus A this, then what it is? It is what is this B minus A f star? The length of this, it is just u e u star length, but then this is just length of E square. Why this is? Can you tell me why this is? Because when you do this trace of u e u star, what is this? This is trace of e u star, then star of it, so it is u e star star. So since u star u is identity, so it would be u e e star u star. But then you use the property of trace, that trace of ab is equal to trace of ba. So it is actually trace of e e star. So this is equal to this one. But what is this one? What is the length of e square? It is this one, I equal to 1 to n. But then the way we have chosen this, what it is? It is epsilon by n plus and so on plus epsilon by n, which is actually equal to, sorry, not equal to, but less. So this is equal to epsilon. So clearly we have found a matrix B such that length of B minus A square is less than epsilon. The only thing is to check whether B is diagonalizable with distinct eigenvalues. Now is B diagonalizable with distinct eigenvalues? So this B is actually what you can do. This B is this one. If you look at it carefully, I have chosen this B in such a way that this is U star AU plus E times U star. This is your B. Now can you see from here that B is diagonalizable with distinct diagonal entries? With distinct eigenvalues, sorry. Can you say from here that B is diagonalizable with distinct diagonal and with distinct eigenvalues?
Yes, sir.
Why?
Because U star AU is nothing but T, and T plus
Right,
T has distinct eigenvalues.
right. Because U star AU is T and then E is just a diagonal matrix. So this remain when you take the sum of U star AU and E, this sum is again upper triangular where the diagonal entries are this EII plus alpha I. And then this matrix is similar to because you are multiplying from left with U and right from U star. So this is similar to this one. So the eigenvalues would be same. So so this B is diagonalizable where the diagonal and where the eigenvalues are all distinct, and this completes the proof. Now this you can see why I have chosen these alpha is in such a way because I wanted to this relation to satisfy. So based on this you can you can write several as I mentioned you can conclude several statements for diagonalizable matrices or for invertible matrices. Let me give you one exercise here. Or before I give you an exercise, let me ask you this question. In the proof of Cayley-Hamilton theorem here, or in the statement of, I'm sorry. So in the statement of Cayley-Hamilton theorem, I said that here every matrix satisfies its own characteristic polynomial, right? This one. Now, what is wrong in the following? So let me write it here. What is wrong in the following? So you know that the characteristic polynomial is just determinant of sorry lambda I minus a. Characteristic polynomial of a is this one, and we are saying that this is 0. Now if I just replace lambda by a here, then it gives me a I minus a, which is a minus a, so it is obviously 0. So then it is very straightforward. What is wrong in this argument? Or let me write this as a question for you. So what I'm saying is the following. So the question is, you have to find what is wrong. You have to tell me what is wrong with the following in the below argument, or what is wrong in the below argument. So you tell me what is wrong. So what is the argument? Since we know that PAT is determinant of lambda I minus A, what would be PAA? It would be lambda determinant of AI minus A, which is determinant of A minus A. The determinant of 0 is 0, and therefore PAA is 0. Now, what is wrong in this argument? First, you tell me, is it correct? If this is correct, then the proof is very straightforward. Proof of Cayley-Hamilton theorem is very straightforward. But this argument is not correct. What is wrong?
So because lambda is an eigenvalue of A, then must belongs to field.
No. So here in this, you cannot say that it is an eigenvalue. We are just writing this as a polynomial. So lambda is an argument for this polynomial. So it is a polynomial in lambda. And when I say that you just replace lambda by A, then you write it in this way. I mean, if I do it in this way, then it becomes this. What is the problem here? Eigenvalue argument will not work here. So what else we can say, or can anybody else tell me what is wrong in this? Anyone? I'm telling you that this statement is wrong. I cannot do it in this way. This is mathematically incorrect. Where do you see that? Which step? So this is clearly the step where I'm where I'm making the problem is here, because other things are like they are mathematically fine. If this is true, then this is true, and this is true. This is the problem. Why this is the problem?
सर
This
अल्फा
is
लैम्डा स्केलर है
sorry, lambda स्केलर है तो
मैट्रिक्स सर ये फील्ड से होगा
yeah.
तो
So
ये तो
what
फील्ड से
if you do? Yeah, if you look at lambda I minus a, what is lambda I minus a? If you look at this, it is lambda lambda. This is the lambda I and then minus a. Now, if you want to replace lambda by a, then it will be this one. So these matrices are not of same size. So you cannot do it in this way, right? So this doesn't make sense. So this statement, if you just blindly use this one, then it won't work. And therefore we need that proof. Okay, so I'll stop here because I'm having some problem in my throat. So I'll leave you today early, 10 minutes before. In the next class, I'll take 10 minutes extra. So again, I'll remind you that tomorrow is a quiz. The quiz will start at 3 o'clock, the same way as I mentioned in the email, via grade scope. And your major exam is on 17th in the first half between 9 to 12. So I'll send an email regarding that. The syllabus is everything for the quiz, for the exam, for the major exam. Whatever we have covered in this course, uh, mostly it would be from what we have covered after minor exam, but there would be a portion from what we have covered before minor exam also. Okay. If you have anything to ask, anything to say, then
Sir, in the quiz, what is the syllabus?
in the quiz, whatever we have covered after minor exam, I have mentioned this in my email,
So, including today's lecture.
including today's lecture. So you want me to
The
include
unit,
today's lecture?
No,
If you
sir.
want, then
the
I can include
unitary
it.
mat.
Yeah.
Sir, how to find unitary matrix U of Root's lemma?
Or
So, like example.
I have
So one
I told you in
example
the
based on
I have told you in the last exam, in the last lecture, there is a way. It's like sorry. So it's like you have a matrix A, and then sorry, you can find this convert this A into an sorry. So let me first close the recording, otherwise your recording would be very annoying because of me.